Okay, in this video I just wanted to mention briefly how to convert some of our code so that our differential equation solver works with a vector as well as a scalar valued function. Okay, so first off, we have a function here. By the way, I've got the code here zoomed into the Octave online so you can see what it looks like. Hopefully you can read the code there from the screen. And now I need to change this. My func right now is just y prime equals 3 plus t plus y, and I want to change that to the third order differential equation from our notes. That was the last video from, gosh, was it Monday? I think it was Monday. So I'm going to write in a few notes here about what I want to make my differential equation into. So I've already got it typed up here. So I'm solving y triple prime plus y times y prime equals y double prime plus cosine of t. And so just as a reminder on how to do that, we have to substitute some new variables into the differential equation to make it into a system of differential equations. And so we have x1 prime is equal to x2, x2 prime, which would be y double prime, is equal to x3, and x3 prime would be y triple prime, and that is the differential equation up here, right? So move everything else over to the other side, and we have minus, let's see, y was x1, y prime was x2, so this is minus x1 times x2 plus x3 plus cosine of t. Okay, so now I've got a system of three derivatives here, right? And so the idea here is I want what's coming in is going to be a vector in R3, and so what comes out must also be a vector in R3. Okay, and so one way to do that, or to force things to be the same size, is to say something like dy equals zero's size of y. Okay, so that's going to be forcing the output to be the same size as the input. Okay, and now we just we're just writing down our three equations here. So dy1 is equal to dy2, or sorry, what is it? Y of 2, dy of 2 is equal to y of 3, and dy3 is equal to minus y1 times y2 plus y3 plus cosine of t. Okay, and then that's it. Double check to make sure no t. Whoops, I've got a 0 there instead of a minus. Okay, is everything else looking okay? So we'll save that. Okay, and so the important thing again is that the size of the input is equal to the size of the output. Good. And now let's go back to our Euler forward function, and let's see if we can change this so that y init, if it is a vector, then everything will work properly, because right now we have it set up so that y init is a scalar, right? And so one thing we can do then is I need to know what the dimension is of y init, so let's go ahead and stick in a line here. M equals the length of y init. And so, for example, if y init is in R3, then the length would be 3, right? And then, so I'm going to be forcing my function to be, or my solution here to be a column vector in R3, for example. But it could be a row. Should we have a column or a row? Let's try well, we could try both. Just for fun. And so I'm going to go ahead and think about things in terms of columns, and so my data storage will be in y, right? So that's going to be m rows and n columns, one column for each point in time. And then we will set up our initialization here. So this is now the first column of y, is y init. And then we go into our loop. K1 is going to be using f at ti and y as a column, right? And then this is going to be a column. and this is going to be a column vector. Good. So is K1 a column? It sure is. So everything should be defined appropriately here. Very good. Okay, so let's save that. And now how do I use this piece of code here? Well, let's go over to the command line now, and we'll define some of our initial values here. So how about my y init, in this case is the 3 vector, by the way. So let's make y init maybe 1 with a -1 and a 0. So these are the values, by the way, of if you remember myfunc. Do you remember what the values of the derivatives were? The first one was y, so that's the initial position. Second one is initial velocity, and the third one is acceleration. Okay, and so in this case we're setting things up so that we have an initial position of 1, an initial velocity of -1, and an acceleration of 0. Good. Time 0 will be 0. These would have to be given to you, right? The final time would be maybe 1, and let's take a step size of 0.001. Okay, and now we'll call our Euler forward. Euler forward with the name of the function at myfunc, and then we'll have our t0, our y init. I guess I should have said y0. Well, that's okay. TF for t final, and then our h. Good, and that computed everything, I think. Let's take a look. Now if I type in just t, the numbers kind of go everywhere. So if I put t prime, that's a t transpose, and you can see the values a little bit better. And so here you can see all the values of time. We had quite a few because the step size was so small, right? Okay, and then we can plot. Let's see. Here's a nice command to remember: WHOS, and that will it's kind of a size who. Because if you just type in who, you'll see what variables you're using. But if you type in who with an S, it tells you what the dimensions of everything is. And it's really important to keep dimensions straight in Matlab and Octave, because if your dimensions are straight, then things are probably being computed correctly. Okay, and we see here that we have our y, and we see here also that the first row of y is going to be our solution, right, that we want to plot. So let's go ahead and plot t with the first row of y, row 1 and all column elements. Okay, and then if we plot that, oh, that looks pretty nice. Good, very good. Now, I said that we could use rows instead of columns, and so how would that change in your code? What would you need to change? So let's take a look here. Euler forward, I think, is the only thing that you need to change if you want to use rows instead of columns, because now what we would say is our m and our n are fine, but we would just swap them out. And so we would say n here and m here. And here's a hint: if you want to force something to be a column vector, let's see. Let's go over to the command line, and let's see if we can force a vector to be a column. Because I might say, for example, y equals 1, 1, 1. 1, 1, 1. And so that's a row. And so if I do y with parenthesis with a semicolon end parenthesis, that forces it to be a column, right? And if y was originally a column, then y with the colon there also is a column. So if you do y with a parenthesis column, that kind of forces the vector to be a column. So we want to force it to be a row, and so we will do the colon trick, but then we will put a transpose on the end. Oops, where am I? I'm typing in the command space instead of here. Good. So this forces, let's go ahead and put a note here, forces y, I need to change that line, y to be a row. Okay, and so this would be y1 comma colon. Good. And now this is yi comma colon, because it's a row now instead of a column. And this is I comma colon, because it's a row. And this is a row. And I think that's it. Good. Because now I think myfunc will automatically do rows instead of columns, right? Because we said that the output should be the same size as the input. So let's give that a try. Let's see if we solved that problem. And so I'll reinitialize my stuff here. I'm using the up arrow key to scroll through my old commands. So that's a little hint. I think I need to redefine these. So I'm making this a row now instead of a column. I guess I did force it. And now we will call our Euler code. Where are you? There you are. And enter. Good. And now whose? And now do you see what happened? Your y is now 1001 by 3 instead of 3 by 1000. Okay, and so now when we plot our solution, it will be plot t with y and then the first column, right? And there you have it. Good. Oops, sorry about that. Now, I wanted to finish on this note because this is actually how you would call Matlab's built-in commands as well, because the built-in commands actually assume that you do have rows instead of columns. And so, for example, we could call the built-in ODE23. That's always a popular one. And so we would have our at myfunc, just as we did. Then what we would do is, we have a t span here. So we have t0, we have a vector with the initial time and final time. And then we have our y initial. And what you don't have here is you don't have an h. You don't have a step size. And that's because when you use a 2-3 method, the solver is going to go through an order 2 locally and then an order 3 locally and do an estimate of the error. And if the error is too big in some places, it will cut the step size down automatically. And then if the error is too small, it'll allow a bigger step size. So we have an adaptive step size method here. And so let's go ahead and hit our return here. And now we can type in whose, and just to see what things look like. So the ODE23 routine only used 14 points. So let's go ahead and plot now our t and our y. And actually, let's plot these as red circles. So that's an O, not a 0. So that's an O, not a 0. And then a hyphen there. And let's see what that looks like. Because you can kind of see when you're looking at the plot, our window is kind of zoomed in here, but you can see initially, right, we had to use smaller step sizes than later. Later on, we used big step sizes because the error was estimated to be a lot better out here, so we went ahead and got a bigger step size. And then at the end, the step sizes started to decrease again. Very good. So in this case, the output t values are not equally distributed like they were for our method, for the Euler method. Good. So that's how you change your code to work with vectors. And so just as a reminder again, our code that we're writing, the Euler backward, Euler forward, Euler improved, and the Runge-Kutta you could write them either way for rows or columns. But since we're seeing that the Matlab built-in functions are row-wise, you might go ahead and do rows, although it doesn't matter. You could do it either way. Okay, excellent. I think I've probably gone over time. I will see you later.